Hey, Shona, Philip, hope you guys are doing well. I'm sending you this file here, the one you're looking at. It has instructions on what I think we might go. So basically, we go to ISO portal and then we download data. And right now we are focusing on TW. and and then later on we might expand what we do to other stars, but right now TW is what we want to do. And for TW we want to find accretion rate during these years. Data have been available. We want to be able to use weighting to determine that. We want to be able to use the emission lines to figure out if there is inflow, outflow, and how those things vary over the period, the observed period. Um, I think, and the steps that I'm using and the whole architecture that I'm suggesting here is the one I used 15 years ago. So it might be completely outdated, and Ognian and Lee Rottler might be able to come up with better way of dealing with the volume of data we have. So just think about it. So if you take one spectrum that goes from 3,000 to 9,000 angstroms, in there you have several things that you can you can get information. You have the emission lines, H alpha, H beta. You have helium. We have forbidden lines. So right there, just four of them. If we have enough signal all the way to the H and K region, which is 3,900 angstrom, then you have a couple of other two emission lines there to take a look at. But basically, helium lines, H alpha, H beta, the triplet calcium in 8,500. I don't know if it is in there. But anyway, so those are emission lines. Now, out of the emission lines itself, you also have the absorption lines where you can use to derive veiling parameter for that particular observation. So this is just one spectra, right? Now, we have 92 spectra. So you take 92 multiplied by these different measurements, and then you can start having a grip on the amount of data we need to manipulate. And since we are dealing with a bunch of information, what we want is not information you can derive in one single observations, but how that information has been changing over time. And then we can build a story, and then we can tell a story of what's going on with that star. Now, I would imagine towards when we start dealing with not just TW, but GQ and RW and other stars, we might be able to centralize all that information in one catalog. And I'm calling this catalog BossCat, which is the name we had at in Berkeley when we had data from different stars. But for now, I'm just focusing on TW, and the catalog that I built is a simple one and is in a TXT format. Now, so Lee Rottler helped to take the data from the ISO webpage and download. And once this is done, I think I lost where I was. I was able to bring the data and put it in here. So that's what I got. Now, I had a problem right there, and that was I have TGZ. I think this is compressed data, and here's the FITS data. So the FITS data came, see here with this backslash, and IDL doesn't read that. IDL interprets that as a command or as a way to say, hey, a new command is going to come. And I don't know if this problem is going to occur with you. But what I did, I went to every single fits data and I changed the name manually, putting dots instead of this slash, right? So I did that to the 9-2 stars. And then the next thing I did, I select them. And so I select them and I copy them over in a text edit format. And here they are. Okay, and I use some instruction for Mac that is, I put in the file too. It's right here. That's the instruction right there. So at the end, I have all this data organized that way, and I put this end of file here because this is a key that's gonna tell my reading program, my loop, the number of stars have been finished. So I plan to do the same for all the other stars. I will read them, put in a fits format, and end of file towards the end. Okay. Now, the ideal routine that I use to read these fits files, and fits file comes with a header and with the binary information that includes wavelength and flux. So I read that with this program MRD fits. So basically what I did, I create a string variable named catalog Ferros TWHYA which is exactly this file right here, right? And then what I do next is to read all this information here. So each row is the name of one of the files or one of the observations. So each row is the name of one observation. And I'm taking each row and I put it in this array. It's a string array. And towards the end, this string array, and I show you here. So help array has 94 members or elements, not members, elements. So the first one is nothing, and the second one is the first data. So the last one is the end of file. So then what I did, I wrote array in a new array file. I could call this array too. Array is equal array from 1 to 92. It wouldn't matter, but I just put a different name. Now, one thing we want is what I'm trying to say. Probably the only information that I remember I need now from the header is the Julian date. Is when the observation was done, because we wanna study the variation of these features on a timetable. So I need to read that information out, and this is what I did for that. I create a loop that goes through this array, through all these files here, and take the wavelength, it's right here, and take the spectre right here. Now, when I use IDL in 15 years ago, I didn't have this type of structure. But now Python has, and you guys might know, and you guys might be comfortable with that. But right here, I'm extracting the Julian date using this command fxpar parameter, which go through the header and then look for the Julian date. and then I create a save set with the .sav extension that consists of wavelength right here, spectra, and the Julian date. So I have that information. In other words, so if I go here in my ideal coding, you get one of the star. Let's say this one over here. If I do restore this TW HIA 92 say. So what I have is, let me extend this here. What I extend is I get the Julian date. It's right there, and I get the wavelength, and I get the flux, and I can plot that. So I can restore print Julian date, and I want you to plot WS divided by mean S, and this is what we got. So all of this is some junk. You have H alpha over there. I mean, and you have the Julian date being plotted in there. I can probably establish the range I want to see: 6,500, 6,600. Oh, what did I do? Oh, I need to put an equal. There you go. And then you have the H alpha right there. Okay. It's a heck of an emission. Okay, now that we can, we have all this data in .save format. And see, I really don't need that. I could have that in FITS format and do the same thing, but I'm old school and I'm trying to do what I did in the past. Perhaps that's not the best way to approach, but it's one of the approach. Now let's say we wanna run through the data set and we wanna create movies so we can see how this line change. So then I have these commands. Which is right here. So I want to see H alpha changing over time, and I already did that. So I'm just going to pull up. Let me see here. 6562. No. There you go. I think that's the one. So this is the H alpha changing over time. And this line here, it's not well done. I have to fiddle and tweak this code so that I can have this line going all the way up here. I could create a band and put a different color showing here's the line center. So pretty much the line is not symmetric, is very much not symmetric, and that gives the information of what type of flow we are seeing. Is an inflow, is an outflow, is the system kind of a tilted or not, and also these different features you can see in the line peak indicate that some opaque sort of a gas is absorbing that central peak somehow. But let me make it more symmetric. So perhaps this should go it's right here. Plot 6580. I think 65 is 80 is good. Let's see, it's 0 is wide. This is good. Let me see if this is better. Probably is better. Oh, this is not good. Okay, so I have to fix that. So this should be probably 90. I think it's better 90, right? 90 makes more symmetric. Unless I go, yeah, I'm gonna go 90, and this missing set 5, maybe 70. Yeah, I'm gonna go 70. I guess that's it. Yeah, better. So then you can see each alpha variant again. I have to tweak this thing here, or it could do better. But you see how much information you can play around. And then in the instruction, you can also check another region, that is where helium line is 5876. Pull that up. I already did that one too. There you go. So it's more, there is a broad component you can quickly see. And these emissions here, these spikes that comes here and there, they are cosmic rays hitting the detector, so you have to eliminate them. So they are not real data, basically. But you have a nice set of absorption lines here. Those are photospheric. You can use them for veiling determination. So that is your helium lines. And I don't know, I haven't correct this star for radial velocity. So it's not pretty much centered in, so this star is not correct for radial velocity. So it's a little bit shift. I would imagine this line should be more central than anything else, since the helium line is almost nicely symmetric. It has two components, has a narrow component and has a broader component. So that's so much for the helium. I think I also put in the instruction that you could look at this helium line, forbidden line, 6003. The forbidden line, I don't think it's there, but what is interesting about it, you can see nicely the absorption lines, the photospheric absorption lines. Let me bring that in. It's right here, I think. There. See this photospheric line? So that is what you're going to be using for veiling determination, basically. So see, these lines are somewhat constant. There are some changes. There are instrumental changes, basically. So the instrument or the data reduction were not well done. So, but you could also think that photospheric lines, they shouldn't change over time, unless there is some activity going on, and the line should be sensitive to that, and you should be able to do some analysis of that. But I wouldn't go at that level of detail right now. But just saying, this emission here, it could be the forbidden line, the stellar forbidden line, but also could be it could be telluric from our own atmosphere. So my intent is that you can take this week and maybe try to reproduce these, and if you have the time, what would be nice to do is to have, let's say, H alpha, H beta, the helium line, and another line, or only a forest of photospheric lines. So 4 different windows um, uh, running this movie at the same time. That would be cool. And then we could create this animation, thinking that in the future we might have our own web page with current development of our research and what you guys finding. We could we could think in make it public that way and create a blog with science information. That's what's instead of having the pressure professional astronomers have that we have to publish a paper and submit and go to referee and all of that, which we can do. I mean, if you guys want to go for, and if we have enough time and dedication, and yeah, we could do that. But we can also create a blog of our science citizen initiative and create a blog. And in that blog, we every 2 weeks or so we update with current research, and then we publicize that among professional astronomers and have them visiting. That would be cool too, but or not. Lee might be thinking, yeah, no, you don't want to do that because you are passing information to the professionals. They will use it. Well, that's true too. But anyway, so let me know. For the next week, I would like to send a series of new instructions. And for next week, this is what I would like to do: is having all the spectra. What should we do to make the spectra um, uh, calibrated to the observer rest frame? Which means, how can we take all these absorption lines or emission lines and make them um, displayed with an array of wavelengths that are set to represent the rest frame, which means hidden line is 587 uh, 5875.621, something like that. And so how do we do that? So I think what people do usually is, I mean, there are routines that you can read information out of the header and then automatically do the radial velocity correction. So we can do that. But I'm not going to do that because I'm lazy. But you guys should do it. It's a good exercise. You can use the T-mid feature here. Where is it? The one we use to read the Julian date. We could use that to find the needed information to make radial velocity corrections. So basically, we want to find where Earth was, what time it was, because Earth rotates, so you are adding radial velocity there. Earth goes around the Sun, you are adding projection to the radial velocity. We are at a certain latitude, that adds as well. And then, so you take all that information, you read that out of the header, and then you say, okay, now we can make correction to the sun's rest frame, and then you do the correction. Another way of doing is to do a cross correlation with the solar spectra. So you take the solar spectra, which is already at rest frame because the sun does not significantly move with respect to us. So, I mean, the sun the solar spectra usually is at the sun's rest frame, and which means a laboratory basically. So you take that spectra and use that to calibrate your data. So you take the TW data and then you cross correlate, match, make sure all the lines are matched, and then you find the rate of velocity. And then what you do, you correct every single region by that same radial velocity. And then you can do a follow-up analysis, whatever analysis you want to do, either veiling or you want to look at emission lines and try to decompose them, break them in different components. That's a more specific work. So for next week, let's try to do the radial velocity calibration and or correction and try to initiate veiling calculation. Okay. All right. Okay.